Thank you, Arshan. Okay, so an adjacency matrix for this particular graph basically says that there is a zero in this matrix wherever there is no edge between the two edges, two vertices. So let's initialize our matrix. So this would be a matrix of 4 vertices where none of those vertices are connected to any other node, right? But in our particular graph, let's say we have this sort of a graph where red, that is number 1, is connected to 2, 4, and 3. So we would basically have an adjacency matrix with ones in the locations for 2, 4, 3, and 4. So for vertex 1, it basically means vertex 1 is connected to vertex 2, 3, and 4. It is not connected to vertex 1, right? So next we can go to number 2. Number 2 is connected to 1 and 4. So basically we would just have an adjacency matrix for number 2 like this, where number 2 has edges in number 1 and number 4. Similarly for number 3, we see that number 3 is only connected to edge vertex 1. So we just have the 1 there. And finally for number 4, we see it is connected to 1 and 2. So for number 2, we would also have a connection. For number 4, we would also have a connection for the vertices 1 and 2. So this would be the corresponding adjacency matrix for this particular graph that we have here. Does everyone understand how we can represent a graph as an adjacency matrix where both of those number of rows and the number of columns are vertices, and we have a 1 if 2 of those vertices have a edge between them? So if you understand, tell me what would be the what would be the space complexity of saving this data structure. Let's say that I have V vertices and I have E edges. What would be the space complexity? So how much space would I require if I have V vertices in terms of V and edges, or E, and E edges? How much space would this particular representation require?
Wouldn't this be V squared?
V squared, right? Because we have both V and V, so V squared, exactly. Okay. Now, the next way that we can represent a graph is something called, not an adjacency list, right? So it is called an adjacency list. So this is another representation where we have vertices, but for each vertex, we have a list of edges from which this vertex is connected to some other vertex, right? So for an example, let's look at our old example again. Let's say that we have this particular vertex, this particular graph, and in Notepad. Could you cut it down by not including the edges to itself? Brian, let me come back to this thing in a second. So an adjacency list would basically look something like this, where for each vertex I would have a set of lists. So for number 1, I have a list that says it is connected to 2, 3, and 4. So I would say the first vertex it's connected to is 2, then the next vertex it's connected to is 3, and then 4. For number 2, I have 1 and 4. So I have 1, and then 4. Right. So for every vertex, I'm basically assigning a list where the list is basically the list of all vertices that this particular vertex connects to. So for number 3, I just have 1. And for number 4, I have 1 and 2.
Just a clarification, that where you have like the 2 pointing to the 3, that's not like representing a connection between 2 and
no, you are correct. That's a very nice observation. So when I write something like this, when I say 2 is connected to 3 and 3 is connected to 4, it does not mean that I'm designing the graph itself using linked lists. I'm saying that from 1, these are the set of numbers or set of vertices that are connected to 1. So this has no relationship to the graph itself. It just says 1 can connect to this set of vertices, and since this particular set of vertices can be variable, can be of variable length, that is why we are using a linked list to represent them. Think of it as an array.
Right. Okay.
Okay, so Brian is asking, could I cut it down? Okay, I'll come back to Brian again. So does everyone understand this adjacency list representation, or any questions? If you understand, what is the space complexity of this? In terms of my vertices and edges, what would be the space complexity of this representation? Now, Brian was asking, can we cut down our adjacency matrix so the adjacency matrix says that which vertex is connected to which other vertex, right? So it means that 3 is not connected to the node itself, that is 3. But if I do have a 1 here, that means that 3 is connected to itself. So that would basically make it into a cyclic graph. But essentially that means that we can have an edge that looks like this. And in the general terms of the graph representations, we can have this self loops as self edges for this particular graph. So that is the reason, Brian, that is why we do not remove the matrix diagonal in order to cut it down to more. And again, yes, as you're correct. At the end of the day, it will still be V squared. So I have V plus E, and I also see V times E. So does everyone understand how it is V plus E and not V times E, the space complexity of this particular adjacency list representation? So basically we have edges for every vertex, right? The number of edges for every vertex. So the total number of space these linked lists take up is going to be the number of edges, right? Because it is going to be 2 ways, right? So let's say take one edge from 1 to 4 and take the other edge that is from 4 to 1. So each vertex, each edge takes up 2 spaces. And since we have 4 vertices, we need 4 such lists. So together this makes up into big O of V plus E. Right, so the space complexity for this particular representation is V plus E.
The adjacency list is important because we can have like very sparse adjacency matrices in like such as like Facebook with your like friends and stuff.
Exactly. So that is the decision that you guys would make when you're coding something. Are my vertices too small? And if it's a complete graph, let's say that I have a few vertices, but all of them are connected to every other edge, every other vertex. In that case, it would be better because it's a more complete and dense graph. In that case, it would be better to use the adjacency matrix representation. However, if I have very sparse graphs that have very few edges, then it would be better to represent it as an adjacency list, right? Because there are issues. So before we begin, so the space complexity for a adjacency matrix is always going to be larger than an adjacency list, right? You guys understand that? Because this is essentially V plus E. At max, I can have multiple self loops, but at that end of the day, I can't get to V squared, right? But it also means that since I'm representing this as a list, we need to now spend more time to figure out whether an edge exists or not. So in case of an adjacency matrix, let's say I want to know whether there is an edge between 2 and 4. Right, what I need to do, I just need to go to the cell location 2, 4, and I see there is a 1 there, so I can say yes, there is an adjacency, there is an edge between 2 and 4. But for an adjacency list, I first need to find out this particular location, so that is row 2, that is fine. But then I need to read through this entire list one by one in order to figure out if 4 exists or not. So that makes it a V plus E complexity to figure out whether an edge exists or not. Does that make sense? Yes. So one is we can check whether the particular node, particular edge exists or not by theta one time, and the other one takes basically n time, where n is the number of edges that we need to iterate. So one takes up less space, but the trade-off is it requires more time to get it. Okay, moving on. So as someone brought up about dense graphs and sparse graphs, so if you have a graph that is represented with multiple edges and every edge connects every other vertex, every vertex is connected to every other vertex, in that particular scenario, we would call that graph as a dense graph because edges are close to being n squared as the number of vertices that we have. Now, the other case would be a sparse graph where edges are close to big O of n but fewer, right? So in that scenario, it might be better to trade off one over the other. And that exactly how your graph is, or how your graph is actually how your graph representation is, that would make you choose the right algorithm to solve this particular any particular graph problem. Okay. So the first problem that we are going to look at is called depth first search. So depth first search is an algorithm that figures out if a graph, so basically it searches from a particular node of a graph and traverses this entire graph one node at a time. Right? So this gives you a lot of information about the particular graph. So that let's say that somebody has given you a particular graph in some of the representation, in some representation. Let's say that they can either choose adjacency matrix or an adjacency list representation. Somebody has given you some graph. Now, what you need to do is do some analysis on that particular graph and figure out some components of that graph, right? So DFS is a very nice algorithm that allows you to search through and figure out which parts of that graph are reachable from a given particular vertex. So remember that we can have graphs that are completely connected like this, where every vertex is somehow there is a path from one vertex to another. However, we can also have disjoint graphs that, and this diagram will come up later, but we can also have disjoint graphs where we can have the first piece of graph here, and again within the same graph we can have some disjoint set of nodes that where K and L is only connected to each other, but it's not connected to the larger graph. This is also, this entire thing is also one single graph, right? So DFS gives you a very nice way to figure out that given a particular node, if another particular vertex is reachable from that particular node or not. So if I run DFS on this particular graph and I say that my starting node is D, let's say my starting node is D, I can then, after running DFS, can claim that L is not connected to D or K is not connected to D. However, F, I, J, and blah, 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 all of those nodes are connected to D. So that is what I mean when I say reachability in a graph. Okay. So the usual algorithm that people use to first understand DFS is, first we need to figure out that given a vertex, can I find out what other vertices are connected to this particular vertex? So when I say connected, I mean there is a path somewhere that connects those two vertices. So let's see. So in this example, D and J are connected. There is no direct edge between them, but there is a path between them, right? Okay. So let's say that we have this particular algorithm, and let's go through this particular pseudocode one by one. So this particular pseudocode is called explore. It takes in two things. It takes in a G, so that is the graph representation itself, and it takes in a starting vertex V. Given this starting vertex V, Brian Nees, what do you mean by the time complexity of DFS is big O of n? What is n? Is